is a nice paper that kind of adds more meat to one of the earlier papers on this topic. Obviously, I'm a co-author on this paper and the one that came before. The earlier one said the number of cyclones during El Nino and La Nina have been interpreted as the warming and the expansion of the warm waters and so on. But it turns out that the numbers actually don't change that much, and it is related to the fact that the winds that change during El Nino and La Nina, they don't just determine the SSTs and their distribution, location, etc. They also have what is called wind stress curl. So they have a rotational effect, so they can churn the ocean in clockwise or anti-clockwise directions, and in the northern hemisphere anti-clockwise winds will lift the so-called thermocline, or it can reduce the hurricane potential, which is called the water above the 26 degree isotherm. I'm explaining that with words, but we'll see some figures. It's important because the cyclones get their energy from the ocean when they are propagating or moving along, and when they hit land they often tend to break down into pieces and die away because there is no water to give them energy. There is not enough soil moisture to feed the convection, the rising air, cloud formation, and when clouds condense and produce precipitation, rainfall, that heat is released, right? Evaporation takes the heat from the ocean, and condensation releases that heat in the atmosphere. So if you move the thermocline, even if sea surface temperatures are warm, you can have reduced hurricane potential or the energy for the cyclones. So number of cyclones that get born is severely affected by these, and the intensification of a cyclone that's already born is also affected by how much hurricane potential or energy is available below the surface. So this one took that idea just from El Nino and La Nina to a global scale, and for all years, El Nino, La Nina, normal, and so on. And it talks about the crucial role of subsurface ocean variability in tropical cyclone genesis. So there is always some rotation, there is some wind conditions, there are some wind conditions that are favorable and so on, but unless there is energy available, cyclones are not born. That's what we would call cyclone genesis. So I'll again be brief, but it's a relatively short paper that you can read. The upper ocean provides thermal energy to tropical cyclones. However, the impacts of the subsurface ocean on tropical cyclone genesis have been largely overlooked. Here we show that the subsurface variability is associated with the variation in the 26 degree isothermal depth have pronounced impacts on the tropical cyclone genesis over global oceans. That's the cyclone potential. The sea surface wind stress and its curl, so that's the rotational effect in the winds. So if you curl your fingers in the way winds are changing, horizontal winds near the surface, then it can be downward or upward, and if it's upward, it's pulling the colder waters closer to the surface, so reducing the 26 degree isotherm depth and the cyclone potential, whereas if it's downward, then it's converging water and pushing it down and accumulating more warm water about 26 degrees centigrade. Okay, the surface wind stress and its curl before the tropical cyclone genesis are large enough to perturb the ocean interior down to more than 100 meters due to entrainment and upwelling. Upwelling is where you pull up the waters because waters are moving away at the surface, which means you have to replace it with water from below. And entrainment is basically how the cold water gets sucked into the surface so that the sea surface temperatures can cool if you pull in the colder waters. That requires energy to move the colder waters into the surface, which we call entrainment. Okay, the 26 degree isothermal depth can fluctuate by tens of meters to significantly modify the upper ocean heat content. Consequently, sea surface temperature anomalies under nascent tropical cyclones are induced and tropical cyclone genesis is modulated. So wind stress curl may produce warmer SSTs in a cyclone that's trying to find favorable conditions to grow, or it may cool the temperatures, so you know what will happen if the cooling happens. So our results substantiate an unexpected relation between ocean interior variations and tropical cyclone genesis. This idea of the wind stress curl having so much impact was not being reported, so it just appeared a few weeks ago in 2025. And this is the main message. If you are not a ocean dynamics person, you can take this message and leave, but if you want to learn more, then you can see how things work. Tropical cyclones producing damaging winds, heavy rainfall, storm surges, and inland floods are among the deadliest natural disasters worldwide. In the North Indian Ocean, the numbers are small, but the mortality per cyclone tends to be the highest in the world because of all the vulnerable countries like Bangladesh. India has done better now, but there are other countries, Burma and so on, which are still highly susceptible. During 1970 to 2019, TCs resulted in 779,324 fatalities and 1.4 trillion US dollars in economic losses. As coastal cities continue to become more populated and developed, the need for TC risk assessment and management becomes increasingly critical. The locations and frequencies of TC genesis modulate the lifetime maximum intensities of TCs and exposure to hazards. Therefore, enhancing our understanding of TC genesis is crucial. So, you know, this justification is needed. TC genesis is determined by many environmental properties such as Earth's rotational effect. We have rotating systems because we are on a rotating planet. The atmospheric parameters of low level relative vorticity, that's the rotational tendency. If you have a little seed in rotation, then it can grow into a cyclone. Vertical wind shear, so if the direction of the winds changes from the surface into the atmosphere, it can chop off the cyclone and prevent it from growing, like it happens during our monsoon season. Remember, in our region we have a cyclone season before the monsoon and after the monsoon, and the monsoon is not very strictly a cyclone season at all. And now the question is whether that is related to just the wind, or is it related to how much energy there is in the ocean as well because of the wind stress curl. Okay, that is being studied separately. Mid-level relative humidity, because humidity is needed to condense and form clouds and release condensation heat to take up more moisture and so on, so the cyclone can get stronger and stronger. And atmospheric instability, which is just another way of saying there is energy available to feed the cyclone that's trying to grow. Ocean is the energy source for TCs. Upper ocean heat content is also essential for TC genesis, which was recognized long ago. Based on observations, the ocean thermal energy representing the ocean heat content above the depth of 26 degree isotherm was adopted as one of the 6 parameters in the first empirical model for TC genesis, which goes way back, I think, Bill Gray. However, there has been a disagreement on the influence of the upper ocean heat content on TC genesis, tropical cyclone genesis, and numerical simulations have drawn different conclusions, which is always an issue because models have various formulations and different biases or uncertainties, let's say. The controversy has grown because satellite observed sea surface temperatures do not capture the subsurface conditions. They only look at the top few millimeters to centimeters. In contrast, the impacts of the upper ocean heat content, or generally variabilities in the subsurface ocean, on tropical cyclone intensity rather than on TC genesis have been well examined. So once it's born, it goes in a different directions in terms of its relation to sea surface temperature, but if it's still being born just before it becomes identified as a tropical storm or deep depression, then you can look at what the conditions are. SST was replaced with the inclusion of subsurface temperature information in the potential intensity index, yielding a better representation of TC intensity and improving its forecasts. So it just proved that including subsurface heat content is critical for accurate predictions and intensity forecasts. Nevertheless, SSTs are assumed to play a dominant role in TC genesis in most studies, which is different from the original idea of saying there is a hurricane potential, which is very important. Okay, so there are various reasons why that's generally been ignored, because people assume that the subsurface variability is closely related to the surface temperature. If surface temperature is warm, then there is more hurricane potential available, that the 26-degree isotherm is not a limitation. And people didn't pay attention to the wind stress curl and its impact on the 26-degree isotherm, or the amount volume of the hurricane potential above 26-degree isotherm, as opposed to just sea surface temperatures and assuming they are closely related. In fact, they are anti-correlated in many cases. So that's what we have to worry about when we want to do this correctly. Okay, so here we show that variabilities in subsurface ocean have detectable impacts on TC genesis by examining the genesis stages of 2032 global tropical cyclones over the past 25 years from 1998 to 2022. Essentially, to do this correctly, you have to take all the cyclones that are nicely listed in many data sets. Then you have to go just before they were born. So that's the cyclone stage, okay, genesis stage. And then there are some details on how to see what the SSTs were doing and what the 26-degree isotherm or hurricane potential was doing. So our findings highlight the role of subsurface ocean in TC genesis, considering out of sync warming trends in the ocean surface and subsurface under climate change. It's essential to explore the impacts of subsurface ocean on TC genesis and their evolution under future scenarios. That's a bit of a detail. Essentially, you always see some claims on what will happen to tropical cyclones as we continue to warm, and this conclusion is being drawn using models, climate models, which actually do not even represent cyclones. So we take these factors that matter, like vertical shear and mid-level moisture loading, vorticity near the surface and so on, and we say the cyclones will get more in number, less in number, or that number doesn't change, but the stronger category cyclones will increase, and so on and so forth. All this has been done without considering the subsurface ocean information, and the point here is that that has to be included as well, which means the ability of the models to reproduce those subsurface variabilities also becomes very critical. Okay, what are the significant disturbances in the ocean interior? So I will skip some text and keep taking some salient points according to me, but you can read the paper to make sure you don't miss anything if you are interested in details. Significant disturbances in the ocean interior by pre-genesis TCs. According to the World Meteorological Organization, a TC is born when its intensity reaches 35 knots, or equivalently T2.5 according to the Dvorak technique, which I won't go into. A TC is considered in the pre-genesis stage when its intensity reaches 30 knots, or T2.0 in the Dvorak technique. The first day of the pre-genesis stage is referred to as day 0 in this analysis, and negative days represent days before. So we keep going back to see how the winds were behaving and how that affected the hurricane potential and the subsequent evolution of cyclones. The location and intensities of TCs are obtained from best record, and so on and so forth. So there are some details on how the thermocline actually moves and what kind of wind speeds correspond to what kind of wind stress curls and so on. Let's just look at there is always there are always wind stress curls on a seasonal time scale, let's say, and that determines kind of the mean depth of the 26-degree isotherm, and then the cyclone is trying to be born. So there is a pre-genesis stage where it's, let's say, getting stronger and moving towards 35 knots or 18 meter per second, and the pre-genesis cyclone itself has some winds. Hence, it will also have wind stress curl. So, will the pre-genesis wind stress curl allow it to grow, or will it be in a way that will reduce the hurricane potential to prevent it from growing? Will it have a positive feedback on itself or a negative feedback? Those are the kind of things you want to look for. So let's look at the data, which is easier to explain the things. Climatological sea surface and subsurface environments and positions of pre-genesis tropical cyclones. So we are looking here at the depths of the 26-degree isotherm. The reddish colors here are all 200 meters or so and deeper, and there are standard regions where it's deeper, but sea surface temperatures are, so they are in contours. Indian Ocean has very warm temperatures. The Pacific has warm temperatures on the east. There is upwelling or divergence near the surface, cold waters coming up in the far east, which changes during El Nino, as you know, or if you don't know, you can follow up on my other podcasts. And this entire thing moves back and forth with the sun. But just note that there are warm temperatures and deep 26-degree isotherms in certain places, which means they are likely to be more favorable for cyclones. And surely you see here that there are cyclones. These are the black dots denote climatological sea surface temperatures from 26 degree to 29 degree. Sorry, that's the black contours. In B, we are looking at position of pre-genesis TCs with observed sea surface temperatures. Okay, so what we are doing here is the positions where SSTs are observed by microwave satellites are denoted with black dots. So basically you want to see where you have both pre-genesis cyclone data and sea surface temperature data, and the positions observed by the drifters are noted with purple dots and those observed with Argo floats. So there are some details. You basically want to use as many data sources as possible to make sure that you are getting everything correctly from multiple sources. Okay, so feedback of subsurface variability onto TC genesis, which is what your most important calculation is, to argue that subsurface conditions matter a lot. So you want to look for change in the 26-degree isotherm depth delta D26. Okay, how things change and so on. So here let's just look at a figure again. Change of D26, and there are negative numbers and positive numbers. So you have wind stress curl pulling up the 26-degree isotherm and making it shallower compared to the climatological depth, and you can use a baseline of pre-genesis as well, but let's not worry about it. It's basically shallower and unfavorable, and where it is reddish colors, it's deeper by 10 to 20 or more meters and favorable for intensification. So the ratio of D26 change to its standard deviation gives you additional information on how much the D26 varies by itself without being related to the cyclones, but how it's varying because of during the pre-genesis stage, which tells you a little bit about where there are this is, for example, the region where more than 30% of the global cyclones are born. So that gives you a sense of the scale of this region, as well as the number of red dots that you see in both places. Okay, so responses of subsurface ocean to pre-genesis tropical cyclones: changes in the depth of 26-degree isotherm due to pre-genesis TCs. So this is a change due to pre-genesis tropical cyclones, not before, not after they become a cyclone, but before. So many of them are in fact shallowing the thermocline and or the D26 and reducing the hurricane potential for themselves. And this is, as we said, ratio. And in B, we are looking at the histogram of D26 changes. You can see that a lot of them are it's slightly negatively skewed. So lot of the, so in terms of number of pre-genesis cyclones out of the 2032 that were looked at, a lot of them reduce the depth, and this tail is slightly thicker as opposed to here. So far more pre-genesis tropical cyclones are reducing the D26 depth, because that's negative here, and you can do that here as ratio as well, which shows a similar result. Okay, so you get the idea that we cannot just assume that warm sea surface temperatures are going to keep the cyclone going, but you have to worry about what the cyclone starts to do to itself or to its energy source once it starts to get stronger and becomes gets closer and closer to the threshold of 18 meter per second or 35 knots. Okay, this is the comparison between Ekman layer depth and depth of 20 degrees C isotherm. Basically, some detail that I may not want to go into here. Ekman layer is where the winds that are blowing on the ocean surface produce a certain impact. That's the depth to which the wind effects are going, and 26 degree isotherm is typically below that, but you want to be sure that it is always deeper than that. So here you are Ekman depth going all the way to 600 meters or more. So colored thick lines are Ekman layer depths estimated with various empirical formulas. Each black dot represents the D26 under a pre-Genesis tropical cyclone. So it is within the Ekman layer, much shallower than the Ekman layers, which means wind is easily able to affect the D26. Okay, let's see here. B is the ratio of the estimated Ekman layer depth to D26 under pre-Genesis TCs. So you can see the ratios. There are some details as to how you would want to interpret, but basically these are showing the latitudinal distributions. The equator is here for various climatological wind reasons. The global picture turns out that as you go beyond 5 south, 5 north, you have many more pre-Genesis tropical cyclones. Obviously, the rotational effect is very weak as you get closer to the equator. So if you're standing on the equator, you'll be just going around without any rotation, without any rotational effect. But if you step off the equator, you begin to feel your head spin because rotation becomes important, and that's how cyclones grow. If rotation is weak, rotational effect is weak, they cannot grow. Okay, so you get the idea. For mature TCs, sea surface cooling is known to have a significant negative feedback on tropical cyclone intensification. It means cyclone itself can cool the temperatures by pulling up colder waters and entraining them into the surface layer. A similar conclusion is found for pre-Genesis TCs as shown in figure 5b. There is a statistically significant positive correlation between SST changes and the 90th percentile of TC intensity change rate from day 0 to day 3. Essentially that means here is figure 4, which I skipped, but let me re-look at this. Did we? Yeah, we did 3. Let's do this and go to figure 5. Essentially that means there is in fact a way that cyclones can reduce the energy source for themselves and weaken themselves, let's say, or at least reduce their own ability to keep getting stronger. So surface, the change of temperature here, you can see the reduction in, so it's cooler near the surface, cooling becomes less, and then the cooling goes away, and then you get to deep ocean where the impacts are not felt. So changes in ocean column temperatures due to pre-Genesis tropical cyclones, composite profiles of ocean temperatures. The black points denote the mean ocean temperature changes, which you cannot, so you can see those here. So as you go deeper, basically the change of temperature due to pre-Genesis cyclone gets weaker and weaker, but you can see there is a small impact detectable all the way down to about 900 meters, but it can get significant as you get closer to the surface, and there is this bipolar structure with less cooling close to the surface and more cooling below that, because you have weaker gradients. So there are all kinds of details that you have to worry about. Okay, the blue error bars denote the corresponding standard deviation. Horizontal dotted lines denote composite mean depth. So here is the mean depth, and same as 2a, this is B here, but for temperature anomalies at the mixed layer depth. So there is something called a mixed layer where the wind and heating and cooling effects produce a well mixed layer where density, temperature and salinity variations are very, very weak, and that's called mixed layer because it's well mixed, and then you're trying to mix waters from below into the mixed layer, which requires energy and so on. So you are looking here at temperature anomalies at the mixed layer depth, so you can see negative and positive values again. So whether it's warmer or cooler than before due to the TC genesis and so on. This is the change. This is the change layer, change of mixed layer depth temperature. So the average temperature over whatever number of meters the mixed layer extends to, and this is the change in SST itself as can be detected by satellites, which doesn't correspond always to the mixed layer depth. Okay, lots of details there that's hard to explain in a short podcast, but you if you understand you know what I'm saying. If you don't understand, don't worry too much. Basically focus on the fact that we are actually dealing with subsurface ocean impacts that are generated by the pre-genesis cyclone itself. So here we are looking at significant impacts of subsurface ocean on the genesis of tropical cyclones. So this is change of days. You are going to pre-genesis and then after it's been born. So that's the change in D20, sorry, I'm saying it wrong. This is the change in D26, negative and positive, and this is the change in SST. Okay, which means if you shallow the 26 degree isotherm, the sea surface temperatures tend to cool, which means those colder waters are not only brought up, they are mixed into the surface or the mixed layer. So the assumption that just looking at SST works for us, assuming that the hurricane potential available can be wrong, and if the depth of the 26 degree isotherm gets deeper, then SSTs or the change of SST due to the tropical pre-genesis cyclone can be positive or not affected. So that basically means there is a background state and you are moving D26 from that by the pre-genesis cyclone, and if you lift it, it will cool the SSTs and make it unfavorable for TC growth, and if you lower it, then it becomes favorable and warms SSTs becomes favorable for TC growth. Okay, so this is the rate of intensity change. Similar intensity change is negative if you shallow or cool the subsurface, and positive if you warm the surface, which is again corresponding to deepening or shallowing of the 26 degree isotherm. This is the rate of intensity by intensity change with D26, similar relation. Okay, so essentially the main message is still the same despite my wordy explanation, and I hope it's clear that D26 very closely corresponds to SST changes, which very closely corresponds to intensity changes, which reinforces the message that we must worry about subsurface changes by the winds are associated with the cyclones themselves, especially in the pre-genesis stage, right? The key atmospheric properties, this is the discussion, the key atmospheric properties for TC genesis have long been identified, although there's been no general theory for tropical cyclone genesis. It's empirical formulation we have kept on using, but now we know that we must include the subsurface ocean's role in it. For the ocean, SSTs are found to be important for the entire TC life cycle since they adjust the AC heat fluxes. In this study, we show that the subsurface ocean also plays a significant role in TC genesis. The wind speeds and wind stress curves are associated with embryonic TCs are much greater than those associated with the background normal winds. Thus, they are strong enough to pull up deeper isopycnic or constant density layers down to D26. As a result, the ocean temperature profiles can significantly be modified, leading to either warm subsurface anomalies due to surface convergence and downwelling and heat buildup, or cold subsurface anomalies due to divergence at the surface, pulling up cold waters along with Ekman section, which is the wind stress curl related pulling up of the D26. SST anomalies are produced either by the convergence or divergence and detrainment or entrainment. So detrainment is when you converge water and push the mixed layer down and put warm waters down. Entrainment is when you pull up the cold waters and mix them into the surface water. Okay, it's all about energy available, and these then feed back to the building tropical cyclones. Here we highlight that TC's entrainment mixing as well as Ekman upwelling can be significant during the genesis stage, a notion largely overlooked in existing literature. We demonstrate that contrary to previous perceptions, TC winds are not weak even during the genesis stage, and TC subsurface interactions are already occurring at this early stage, which means you must be sure that they are either having positive feedback or negative feedback, and if you miss it in a forecast, if you don't capture this correctly, you will have wrong forecasts. This is very critical, right? That's the ultimate goal, how to advance predictions and prediction skills. Besides, the previous studies have demonstrated that the TC induced near inertial currents corresponding to upwelling and downwelling are evident in the recovery stage after day 0. Okay, so I already showed these figures. Our study does not deny the effects of other environmental factors such as vertical wind shear or on tropical cyclone genesis. The TC genesis issue is complex and there are many contributors. Obviously, genesis is the joint contribution from all factors, but no single factor is the sole factor. D26 can also represent the ocean stratification to some extent, which is determined by both temperature and salinity. Given compelling evidence that salinity can influence TC intensification, including its ability to suppress cooling by up to 0.3 degrees centigrade, the role of salinity in TC genesis warrants greater attention and further investigation. So here we have only looked at the temperature changes and not the salinity changes, because you can also have rainfall associated with pre-genesis TC, or you can be pulling up fresher waters or saltier waters depending on where you are. For example, in the eastern North Pacific, the thermocline and D26 are relatively shallow, providing less energy for TC genesis. So eastern North Pacific is the Mexican coast and that region, central American coast as opposed to North American coast. Typically, as I pointed out, most of the cyclones are born here. There are very few here. So this is the northeastern Pacific, which is dominated by shallow waters and less salinity, so it's not very favorable. So, however, sea surface salinity is low, resulting in strong salinity-driven ocean stratification, which reduces cooling during TC genesis and potentially promotes TC genesis. Essentially, you have to worry about ocean stratification, which is the density variation with depth. Why is it important? Because how much mixing of cold waters you can do into the surface layer depends on how strong or weak the stratification or the density gradient is. Okay, that's the main point. The impacts of subsurface ocean TC genesis are captured in state-of-the-art coupled climate models. The high-resolution model in comparison project high-res MIP models permit TCs, so the IPCC assessment models do not have tropical cyclones, but there is a high resolution model in comparison project where TCs are permitted, which means they are not fully resolved, but they are born and they can be used for statistics, and they show an improvement in reproducing the observed TC frequency as compared to climate models. The role of the subsurface ocean in TC genesis is estimated with outputs from a 1573-year hierarchy of high-risk MIP model simulations, which is shown in our supplementary table. A deeper D26 indicates greater tropical cyclone genesis number for both the northern hemisphere and southern hemisphere, which is shown in the supplemental figures. It's still challenging to replicate the observed D26 trends in high-res MIP coupled models. The bias in D26 might persist in the future scenarios, which potentially leads to a bias in TC genesis projection. Okay, this also underscores the need to capture the wind responses to continued warming and the associated vertical structures in the ocean to be able to make reliable projections of TCs in the future. So there is the idea of what we are missing right now and what could be affecting limitations in tropical cyclone predictions, and what changes will come with global warming, wind changes, mean depth changes of the D26, and cyclone genesis and its own impact on its own energy source and so on. Okay, so that's a bit long, but that's okay. It's a nice paper, as I said, even though I'm a co-author, but hopefully the points are clear and you can follow up with the paper if you are really interested in more details. Okay, see you in the next topic.